Hello, everyone, and welcome to a discussion on Module 4 in Advanced Machine Learning Techniques. Sorry, I've lost my there we go window. So, Module 4 centers on support vector machines. Pretty cool technology. And so we'll be talking about what it is and why we use it for things like classification. Then we'll talk about, by the end of this experience, you should be able to explain what support vector machines are, so SVMs, be able to apply them, and then talk about things like kernels, regularization, gamma, and margin tuning of parameters. So jumping straight in. What's a support vector machine? And it's basically a way of doing supervised learning with the intent of doing classification, essentially being able to separate things into two different classes. And it's interesting because it not only lets you draw lines between things, but those lines potentially have a width, which is called a margin distance, and it enables us to kind of essentially get a sense of class of future points of how confident we might be of accurately classifying them before we've seen them. It basically uses the concept of increasing dimensionality so that you can do classification of something that otherwise might be challenging to do it. So you can think of it as essentially moving from conceptually from 2D to 3D, and basically using a hyperplane to do the separation of points. That may be in the case of it may be a proper plane whenever you're dealing with going into three dimensions. It could be conceptual as well. So how does it work? And it's about this whole concept of doing a transformation into a higher dimensional space, and you do so by using a function of some sort. And that function is essentially what we mean as the kernel. So it's the means of doing the transformation. There's a linear kernel, which is kind of what you would expect. It's the f of x is equal to b sub 0 plus the sum of ai times x and x sub I, where x is an input vector and b sub 0 and ai are coefficients that you estimate during training. And obviously linear is going to be the simplest in a way. Not everything can be separated with a linear function. So that's why we use things like potentially polynomial functions, where there's something being raised to a power, and exponential or some polynomial anyway, and then an exponential kernel where something is a similar sort of experience of gamma times a sum of the differences of something squared. So regularization, and that's C in scikit-learn or sklearn. How much do you want to avoid misclassification? So this is a direct quote. I don't use them too often, but this was a pretty good way of discussing it. For large values of C, the optimization will choose a smaller margin hyperplane if that hyperplane does a better job of getting all the training points classified correctly. Conversely, a very small value of C will cause the optimizer to look for a larger margin separating a hyperplane, even if that hyperplane will misclassify more points. So it's a way of kind of tuning how important is it for things to be misclassified. When we talk about gamma, we're talking about how far away from the line of separation do you want to consider the points. So it could be that you want it to be relatively close, or it could be that you want to consider all points of all distances from the line. And the idea here is thinking that maybe the ones that are closer to the line might actually be more important than those further away. And so that's kind of a point of considering of, do you want a high gamma, so only things that are close are considered, or you want a low gamma so that maybe multiple things or everything might be considered. And the margin is the separation of line to the closest point. So how far is the line from the nearest points. Ideally, you want it to be in the middle, equidistant, and so that it's does a clean distribution between the two lines. If it's over very close to one side or the other, it may indicate perhaps not a great job of classifying. And it might also be pointing out that you're going to have some challenges when your algorithm sees data it hasn't seen before, because you may very well misclassify. In this case, like those blue squares, if one of them happened to be just a little bit further towards the circles, all of a sudden you've got a misclassification, so you've got an error being introduced. So by making it in the middle, you're potentially reducing the chance of misclassification. Jumping into kind of the demo part of stuff. So another example that I borrowed, and so this is a pretty good article that talks through what is a support vector and why would you use it, and it has a good example here of cows and wolves. So the basic idea is that you've got some things you're wanting to separate from between each other, and so we'll go ahead and jump straight into it. So you can actually kind of see it in motion. And so we're defining a function here that, as the name implies, shows you the results along with a hyperplane of showing where that plane is between the two. So we go and read our data, take a look at our data, and you can see the x's are kind of somewhat in the middle. It's hard to see a little bit here because of the spacing going on with single versus two spaces, but that's basically the idea. And so here what we're trying to do is x's are cows and o's are wolves, and we're essentially working on getting it such that we can actually do our training, figuring out what columns we want, a classifier that we're wanting to use. In this case, we're using a support vector machine with logistic regression and decision tree. So we're doing 3 different types of classification. And so the next step would be to run through it and plot them and plot how each one of them does. And you can see, because of decision trees and support vector machines, do the best, and it's primarily because of the support vector machine is doing so because it's able to take it into a higher dimension space where it's much easier to separate than if you're looking at it in this 2 dimensions. So by applying a transformation on top of it, you're able to see it in see that you can actually separate things in a bit of a cleaner way. This example comes out of the O'Reilly books that we have access to as part of the library, and again does a pretty good job of working through it. Let me get into the right identity here and see if I can get that open. I tried to use different people in Chrome so I can keep track of my stuff, but sometimes it becomes a challenge unto itself. So this is from Machine Learning Quick Reference. Pretty decent, not a bad book. It might be worth taking a look at. So giving credit to where it came from. Start off, as we always do, by loading up the libraries that we care about: Pandas, NumPy, sklearn, from which we're pulling in SVM datasets, and from SVM we're pulling in SVC, and then plotlib, so pyplot from matplotlib, and then some scikit-learn stuff, sklearn, model selection, we're pulling in test train split, which was our tried and true friend. Grid search, which is a useful way of looking exhaustively across for something. And so here what we're doing is loading up the breast cancer data set, and then look at the characteristics of that data set. Always a good idea to be familiar with what data you're looking at. Also, if it didn't already provide this summary, you probably want to take a look at and do some sort of descriptive analysis yourself. That's just one of those things we typically do. Start off by doing our test train split. Seeing what the percentage is, so it's using whatever the default is. And here, as you recall, that C we talked about was, I believe it's the gamma, or regularization, sorry. So how much, how do you want to adjust and avoid misclassification? Back over. So we're setting C to not I don't think necessarily a really large number, and after having done the training, we're getting around 96%, 96.7 on the train set, and 95.8, so pretty close to 96 on the actual test set. And that's with, so I'm trying to see where we're fitting. Trying different kernels here. So this is using the linear does halfway decent. This is actually not quite as good. The RBF. Excuse me. So again, this is where we're doing some normalization, which is always a good idea, and then running it again and seeing that the accuracy went up quite a bit, even with this radio bias function. I believe that's what that stands for. And then moving on, this is one of those interesting sort of things that basically is doing a grid search of using the parameters to figure out what are the best parameters. So you can think of this as a form of auto machine learning, and it is intensive computationally, obviously. So we'll give it a little bit here, but not real long. And you can see, interestingly enough, that having done this grid search at the end, which probably was the first thing the author did, miraculously, the first thing that we saw up there with a linear kernel with C of a value of 1 turned out to be the best. So that's kind of almost like a cooking show sort of thing, where there was some work that went into it ahead of time before picking that example. I'm going to go ahead and kill the kernel just so that it doesn't cause me grief elsewhere. Moving back and on to the next one. And this is an example from scikit-learn. And revisiting Iris this time with some different types of classification. And as you recall, there's a couple of those that are really hard to tease apart because, and frankly, they're probably hard for people to tell apart. So we're defining some functions up here, making a mesh grid, plotting the contours. Then we load up Iris, create our models. And so to walk through, we've got a support vector machine with a linear kernel with C. I'm not sure what C is. Oh, 1 right there at the beginning, with a value of 1. Max iterations is 10,000, and then using 2 or 3 other kernels here, so a poly, RBF, and so on. and this is going through kind of the different types of kernels and kind of what they mean. Yeah, radio basis function. I may have said bias basis function. And that's one of those. These are kind of the normal ones you kind of see. So if we go ahead and start setting up the titles of our graphs and so on, so this is also that we can plot the pretty picture that you see on that page. And the contours kind of show you where the region of each individual classification is. And the white and the red dots are really challenging to separate, as you can see in this larger image. And there's going to be a certain percentage of them that are wrong. Of these, it's kind of tough to even say which one was necessarily doing the best on it. Probably this one. But anyway, it's quite challenging to separate these two in general. It's a reoccurring theme with that data set. Going to our fourth example. Another example from scikit-learn, and this is basically kind of showing the margins separating the hyperplanes so that we can kind of walk through and get a sense of what it does. So this is basically one big script, and it plots and it kind of shows you where your divider is and your margins, and the closest, and it's a nice even split between the two things. So a nice easy to see representation of what we were talking about. So with that, we'll go back to the material. Moving on to the deliverable for Module 4. It has to do with support vector machines, go figure. So the competency is to apply support vector machines for classification of data sets. So you're a chief data scientist at Reliable Dynamics, a robotic development and manufacturing corporation. You've been tasked to classify various data using support vector machines in Python. You are a little rusty using SVM, and you want to make sure your work is accurate. Therefore, you decide to use the scikit-learn library. A machine learning library tool is compatible with Python to refresh your SVM skills. Find an interesting data set by using one of the dataset search engines found under resources, and utilize scikit-learn to apply SVM to classify a group of data sets of your own choosing. Copy and paste your results to create a report using Word. Explain your results, and be sure to explain support vector machines, the use of kernels, regularization, gamma, and margin tuning parameters. So basically the hyperparameters that you use whenever you're using support vector machines. What are they? How do you use them? What impact do they have? If you turn the volume up, what does it do? If you turn it down, what does it do? And so on. The rubric, the first criterion, is a thorough and detailed explanation of support vector machines has been created with well-developed and accurate examples free of error. Criterion 2 is a thorough and detailed explanation of the use of kernel, regularization, gamma, and margin tuning parameters have been created with well-developed and accurate examples free of errors. And then the third criterion, a thorough and detailed report has been created explaining the results with well-developed and accurate examples free of errors. So with that, I'm going to go a little ad lib here as soon as I can find looking for. Let's bring this over here. And what I'm going to show you is Databricks, and in particular, what I'm going to show is the use of AutoML. So to talk through, first of all, what is Databricks, if I haven't mentioned it in the past, and why would you care about it in a machine learning class, right? So Databricks is cloud-hosted Spark. It allows you to run using a notebook paradigm, or you can upload jars and such if you're so inclined, but typically one uses notebooks to perform processing at scale in a potentially big data sort of way. So not just doing data science or machine learning on your laptop or desktop computer, which could be quite impressive, but it's not going to be as impressive as the type of computational power you can bring to bear in something like Databricks. I'm not going to do it, but you can create quite large clusters. So you basically can pick the type of cluster that you're going to want. Standard is one that is intended for many of the typical sort of workloads. You pick a runtime, and there are runtimes that are optimized for machine learning and including support for GPUs. So you can pick a runtime that has both GPU support, and you can pick the workers such that they have GPU support as well, so GPU accelerated. And you can get into some pretty impressive machines. This is a 4 GPU, so not a single GPU, but 4 different GPUs with 440 gigs of memory and a 64 core processor. So and not just that, you can have quite a few of those, as many as you could probably afford to pay for. So that's one of the reasons why to talk about things like Databricks in this space. AutoML is the part that's really kind of cool because what AutoML can do, so I have to go in and create a runtime that is, I'll just call it NML. I need a machine learning runtime. Not going to do GPUs. Not going to do auto scaling. Auto scaling basically will increase the number of nodes in your cluster and decrease them based upon processing utilization. Let's see if it'll let me do that. So what this is doing is, by those few clicks, what I did was trigger the provisioning of a cluster. That cluster is going to have 4 nodes in it. 3 of them are going to be workers. One of them is the driver node. The driver essentially is the manager. It coordinates the work that the workers do. Doesn't actually deal with the data itself, but it tells the workers what to do with the data, so that if at the point that you kick off some sort of processing, the driver tells each of the workers what data they're going to be working on. It keeps track of that in case something happens to them. And then at the end of it all, one of the workers will be essentially tasked with potentially combining together the data to essentially consolidate it and write it out. You don't have to worry about all that when you're using it, but that's what's happening under the covers. So back to the machine learning sort of world. We can start with AutoML, and if it'll, I guess I have to wait for my cluster to finish spinning up. But the basic idea here, and I know it's not fun to watch me wait for it to load, and maybe I'll talk about it on Wednesday. The basic idea here is that you determine the type of problem that you're solving. Is it a classification problem, regression, time series? You give it a data set. You tell it what it is that you're wanting to predict. So if it's what is the value that contains the answer in your labeled data set, and then you give it a name, and then can set some additional stuff. And then what it does after that is exhaustively try the different models that you might think to try. It might even try support vector machine. It probably will do some neural networks of some sort, various types of algorithms to figure out what is the best based upon you tell it as one of those advanced options what it is that how you want it to measure what good looks like. So you tell it, I'm interested in accuracy or something else, maybe F1, whatever metric it is that you want it to most likely maximize, although it could be minimized depending on what you're doing. And you turn it loose. And what it does is using this whole concept of clusters and distributed processing, trains and tests a lot of different approaches, keeping track of each one of them for you so that it can tell you at the end of the experience how well, which one did the best, what did the worst, and so on. And then even at the make it relatively easy once you've picked one that is the best, most likely, to deploy it into an environment to start using it. So it brings a lot of power, flexibility, and what's really nice about it is that unlike a lot of AutoML sort of frameworks, the Databricks framework gives you the notebook that it used to do the experiment. So the way that they approach the problem is to essentially do code generation to create those notebooks with all the different parameters and so on, so that you have a bunch of notebooks that are created. And then if you pick one you like, you have the ability to change it, to extend it, to fix it, to tune it further if need be, or you can choose to just deploy it as is. So pretty cool technology, and is adjacent to the stuff we've been talking about so far. I'm taking of course, the one I can't use is up and running. The other is still pending. The top cluster is a single node cluster. It's basically a pseudo cluster. There's basically no workers, just one driver that also works as a worker. And the reason to do that is if you're doing a relatively lightweight sort of thing, then you might choose to do so. So we can pick the cluster that I have, and like I said, it's either for classification, regression, or forecasting, not time series. I was mistaken. And then you can pick of the data that you've got available to you, the data set that you want to use to do your classification. Looks like I need to import some, so let's go find some data quickly. Do a little wire wiggling here to get this to work. We'll do Iris, even though Iris is not necessarily fun. We'll go ahead and create a table with this UI, put it onto ML, preview the table. Pretty sure it has headers. We have headers, and it can see that it inferred. And what this is doing is very similar to what you would do in Hive, where it's creating essentially a table. It looks like a table. It's sort of a table, and that allows you then once it finishes, it allows us to then go out and target it. Might have a few challenges. You'd have to do a little bit of work because the target is a class, not. There we go. Okay, good. So I can tell it I want to predict the species. Don't think it will really matter. So we can also tell it what kind of metric we're interested in. So as I mentioned, accuracy, F1, and so on. We'll leave it with F1, and you can pick what kind of frameworks that you're wanting to use. And we'll go ahead and start it. And so what it's going to do is run through lots of different options, keeping track of them using MLflow as the means to do that. And that's basically an experiment tracking library that Databricks created. It's open source, can be used, but it came out of that organization. And so at this point it's doing some kind of warming up, getting things ready. The first thing it'll do is kind of a bit of an evaluation of our data. And basically, whenever I set it, I accepted the default that it would train for at most an hour. You can stop it at any point, obviously, and if it reaches a certain accuracy, you can have it to where it stops there as well. But it's going to be looking through for calculating the F1 score for each one of these once it kind of gets going here. Looks like if I click on refresh. And so this is that data exploration notebook. And so they're basically just doing a pandas report on it, sort of concept. It's doing a profiling of it. Literally doing pandas profile. And going through and essentially telling you the number of variables and what's the distribution of each one look like. Pretty handy, especially for not really having to do anything to get it. And granted, it's not that hard to do pandas reporting, but still, kind of a nice feature. And then we've got essentially 25 different experiments have ran, and we can start organizing them by F1 or accuracy. And interesting, we've already got some that are using decision trees that are quite good. So probably something we want to take a look at. So we can actually open up and take a look at the decision tree that it created. And so it tells you the version of the runtime it was being done. And then you can also clone this over into your workspace if you're so interested. Working through kind of what the code does, this stuff is kind of housekeeping, but it tells it the column that we're targeting, then goes through, sets up the MLflow for us, does some imports, It takes a quick look at some directories, and basically this stuff is just kind of getting us up and running of where does the artifacts go and so on. A quick look of the data of what it looks like, and then figure out the columns that can be used, some any kind of pre-processing that we're going to do, the numeric converters that are used, and so we're basically doing some converters and some imputation to handle kind of gaps and such, and then excuse me. Working our way through of actually doing some transformations on that stuff, doing our feature standardization, so standardized scaling, always a good idea. Some the test train split, so this is doing 60% for train, 20% for validation, 20% for test. So it's your typical 80-20, but it's explicitly pulling out that validation set that is used to tune the hyperparameters during the training. So here we start going through, splitting out our data, doing essentially it looks like stratification, and getting to our typical X and Y that we normally do when we're doing classification. Then importing the decision tree classifier and showing you what you need to know about the decision tree classifier. And then we build our pipeline of column selection, pre-processing, standardization, classifier, and you can see what it looks like there. And then pretty much through here is when we do our fit. So we're doing a run, and it's being recorded into AutoML so that we can find the one that is the best. Doing the training, getting back for the validation. Interestingly enough, was not quite as good as the test. So interesting that occurred. And so there's also this ability to do essentially feature importance of figuring out which ones are the more important and who has the most influence. And then if we really want to, we could take this this notebook and actually could deploy it to the for production. So let me here. So you could actually expose this relatively easily. So trying to take a quick look to see if there happens to be any. Yeah, don't really see support vector, but could be in there, and I'm not looking at it long enough. So anyway, that's I think fairly cool. Hopefully you will as well. But a discussion of doing AutoML and kind of a way of doing it in a fast way to potentially get some results. You still need to understand why things are working, but it can give you some nice results quickly. So with that, I'll wrap this up. If you have any questions, let me know. Stay safe, and we'll talk again on Wednesday.